Assalamu alaikum. Today we will be presenting our discrete mathematics final project. The topic of our project was temporal and category based price similarity network analysis, and our course instructor was Rashid Islam, and the group members are Humble Rana, Rehan Ahmed, and me Abdul Rafi. So the table of contents include the introduction of the overall project, the dataset description and pre-processing, mathematical modeling, graph construction and threshold analysis, centrality measures, and then we did temporal relation and hash diagram, and then we applied weighting schemes and influence score, and finally we concluded our project. So in the introduction, I would start explaining the first part of our project, which is mostly about understanding the basic data that we were provided and then converting it into a mathematical form that we can analyze. Now, if we look at the dataset that we used here was the CPI dataset that we took from the website. So what it did was, as you can see on screen, it contained monthly price indexes for different cities and different categories like food, transport, clothing, and many other categories. So each row represents a combination of one city and one category. And then basically, as you can see, we have columns for each month. The data set that we took is from year 2023-2025. Now, what we did was, instead of taking these values as a table, we converted each row into a vector. So basically, which is just a sequence of number, as we can see from our basically the spreadsheet as shown on screen. It represents the price trend of that city for a particular category across time. For example, the Lahore and food category, if we see, has prices increasing like 101, 102, 103, 105, and so on over different months. So this will form a vector, a square matrix contained like 101, 102, 103, 105, and so on. Basically, this is the only step. Now, why we did this? This is done because once it is a vector, we can compare different cities mathematically, which is basically our goal of the project, which we have to see that which cities behave similarly in terms of price movement, and we can achieve this more easily if we use vectors. The next step that we did was normalizing these vector. This is because different categories have different scales. Like if we see from the excel sheet that CPI value for petrol might be 250, 300, or even more. So but on the other hand, the CPI value for vegetables is like 30, 40, 50, or around that. So if we don't normalize these vectors, the categories with larger numbers will dominate the similarity graphs. So what we did was we used a z-score normalization technique, where we make every category have a mean of 0 and a standard deviation of 1. So what this did was this made everything comparable and removed that effect of different scales. So after this step, the all the categories like food, transport, housing, petrol is now on the same level rather than one dominating the other. The next step of So the next step of our project was we calculated the cosine similarity after the vectors were normalized. This is one of the key idea of our project, because what cosine similarity does is that it doesn't care about the actual prices of the categories. So it only cares about the shape or trend the vector or the category is following. So if a similarity is of 1, this means that two cities are moving exactly the same way. So if it is 0, this means that they have totally different behavior, and if the value of cosine similarity is between 0 and 1, this means that they are partially similarity. So this is a perfect measure for price behavior, because this focuses on the direction only and doesn't care about the magnitude. Then the next step we did was to visually see these cosine similarities. We computed a heat map, so which basically compares each city with the every other city. So what basically heat map is and how to read it? It is a basically colorful grid where brighter, or you can say the warm colors show high similarity, while on the other hand the darker colors show lower similarity. So just by looking at the heat map that I am currently showing on the screen, you can instantly identify the group of cities that behave similarly. For example, Lahore, Rawalpindi, and Islamabad maybe have similar trends, so they appear in bright colors against each other. So this is a key visualization, because it gives a quick overview of how connected or similar cities are. So before we build the actual start to build the actual graphs. So to wrap up my part, what we did was we started with the raw CPI data from the from the website. Then we converted that data into city category vectors. Then we applied normalization on those vectors. Then we calculated cosine similarity, so that and we visualized it through heat maps. So this basically part formed the basis of our project for the rest. So to build graphs, analyze centrality, and then examine the relations. So that's all from my part, and now I would like my partner Rehan Ahmed to continue from here.
I'll briefly cover three components, which includes graph construction and thresholding, centrality measures, and temporal relations using a Hesse diagram. Firstly, we begin by converting each city's monthly price data for a category into a normalized vector. We then compute cosine similarity between every pair of cities. A high similarity means their price movement are very similar. To turn these similarity values into a network, we selected a threshold. If similarity is greater than or equal to that threshold, we create an edge between the two cities. After experimenting with several values, we used zero point 0.6 as threshold, which gives a clear structure without overcrowding the graph. What this graph shows is that at zero point 0.6, Pakistan's cities from two major clusters. First one is Punjab cluster on the left, which includes Lahore, Rawalpindi, Gujranwala, and Faisalabad, etc. And the Sindh South cluster on the bottom right, which includes Karachi, Hyderabad, Sakkar, Larkana, and Multan. And we see Banu isolated, meaning its price behavior is not similar enough to any major group to meet the threshold. This tells us price patterns are regionally structured, and thresholding helps reveal this natural clustering. Secondly, I'll discuss centrality measures. To understand which cities are most important in the network, we compute four centralities: degree centrality, how many similar price connections a city has; closeness, how easily it can reach other cities; betweenness, whether it serves as a bridge between groups; and eigenvector centrality, based on being connected to important cities. Cities like Lahore and Karachi appear as influential hubs. They score high on degree and eigenvector. Cities located between clusters tend to show higher betweenness, meaning they connect otherwise separate regions. We also combine these matrices into a single influence score using equal weighting and entropy based method to make ranking more stable. Temporal relations and Hesse diagram. We also examine how these similarity networks change across years 2023 to 2025. We treat each year category graph as a set of edges. If all edges of year A also appear in year B, then A is a subset of B. This creates a partial order which we visualize using a Hesse diagram. Each node represent a year and category like food staples 2023, food staples 2024, and food staples 2025. A line going upward means the later year contains all similarity relationships from the earlier year. What this reveals is whether similarity patterns are stable, shrinking, or expanding over time. For example, if 2023 connects upwards to 2024 and then to 2025, it suggests the price relationships are persisting or strengthening for the category. To conclude, graph thresholding lets us uncover meaningful city clusters. Centrality highlights key cities and regional hubs, and the Hesse diagram shows how these networks evolve over time. Thank you.
So now I'll explain how we analyze the temporal evolution of the CPI similarity networks using relations and partial orders. We defined a relation T between two years y1 and y2 such that y1 t y2 implies the edge of graph y1 is a subset of the edge set of graph y2. So this means that if all similarity connections present in one year also appear in the next, we consider the first year less than or equal to the second. This relation satisfies all the three properties of a partial order, which are reflexive, every graph's edges are a subset of itself, anti-symmetric, the graphs are identical, and transitive, that if y1 is a subset of y2 and y2 is a subset of y3, then y1 is a subset of y3. Now, because of these properties, the relation forms a partial order, and we can visualize it using a hash diagram. In the diagram, each node represents a year category graph, and edges indicate how similarity structures grow or strengthen over time. This shows us whether the price pattern relationships between cities become more connected, more stable, or more complex as years progress. So, moving on to the weighting scheme, which was a weight table or weight values. Now, to evaluate which cities are most influential in Pakistan's price similarity network, we combined the four centrality measures: degree, closeness, betweenness, and eigenvector into a single composite score. We used two different weighting approaches. The first was equal weighting, in which every metric contributes 25% to the final score. So this treats all four centralities as equally important. Whereas the second type of weighting was entropy based weighting. Here, metrics that show greater variation across cities receive a higher weight. Entropy weights help us identify which centrality measures contains the most information in a given graph. Now, comparing these two methods allow us to see how many mathematical assumptions influence the ranking of the cities. This also highlights this also highlights whether influence is driven more by connectivity, shortest path roles, or deeper structural importance. Now, when we talk about the final rankings, which we have shown in the bar chart comparison, we aggregate the centralities across all categories and compute the final influence scores for each city. Now, the bar chart that we have attached below compares top 5 most influential cities under equal weights and entropy based weights. Now, this comparison helps us identify which cities consistently shape Pakistan's price behavior, which cities influence change depending on the weighting method, and whether the network is dominated by major urban centers or evenly distributed. Overall, their rankings reveal the key hubs in Pakistan's CPI structure, meaning cities whose price movements most closely align with the nationwide trends. Now, moving on to the conclusion. In conclusion, our project demonstrates how discrete mathematics can be applied directly to the real CPI data to reveal how meaningful economic relationships are. We used vectors, cosine similarities, graphs, centrality relations, partial orders, and entropy to understand how cities behave over time. Now, this allowed us to model how similarity networks evolve, identify influential cities, and observe patterns that are not obvious from the raw data alone. Now, the overall, when we go through the project, it shows that mathematical modeling, especially graph-based and relation-based analysis, provides a powerful framework for understanding real economic systems. Our study not only met the course requirements, but also produced insights into how Pakistan cities interact through their price movement patterns. Thank you.